line. So in the problems that we have here, the first question was about finding the sample size. And so technically here what it is to know if you remember what the confidence intervals were about there, how to find distribution of a variable from the normal distribution, but from the multivariate normal distribution. You know that the xi's were independent from normal mu1 sigma squared, and the yi's were independent from normal mu2 and sigma squared. So those are normal, so the whole thing is jointly normal. And therefore, the probability that you have here is nothing but the probability that the absolute value of x bar minus y bar minus the difference of the means is less than sigma over 5, which means because x bar minus y bar will now follow the normal distribution with mean mu1 minus mu2 by the properties of the normal distribution and variance to sigma square over n. Why? Because the variance of x bar minus y bar, the variance of x bar plus the variance of y bar, and the variance of x bar is sigma square over n. The variance of y bar is sigma square over n because they have the same variance. That's the reason why you have 2 sigma square over n. And because the problem says that sigma square is known, you don't need to estimate it. That's why there is no t in this problem. And therefore, when we divide the thing that is inside here by the square root of this variance, which is square root of 2 times sigma over n, we obtain this, which is the standard normal. It's not an approximation, it is exact. Therefore, this turns into the probability that absolute value of z is less than root n times sigma over 5 sigma root 2, and the sigmas cancel. So yeah, we don't actually need the value of sigma to answer this question. And so we want to find out the probability, this probability equal 0.9, and that leads us to the number that is here equals to 1.645 using the z table. And therefore, you solve for n by squaring, multiplying by 2. Because of that, you got approximately 136 for n. Questions about this?
You are multiplying with 2 for n.
What?
You are multiplying 2 for n. Why not multiplying 2?
Solving this equation, not just multiplying. So this, that is 5 times this squared multiplied by the 2 that is here to get n.
Okay.
Okay, so that's how we do that. This looks like the other problem where we were to find the n and c, something like that, remember? The previous problem. So my intention in giving you these problems was to make sure that you remain on the topics that are upcoming in your test, not just solve one topic, which was what we did during the week, but still do the things that were on the other assignment, so you can keep track of what we did then and not just forget and start after this lecture to prepare for your test. Now, problem number 2 of that same kind, previous material. You have y1, y2, y3, y4 order statistics of a random sample of size 4, so that's all of them, from a distribution f of x equals 1 over theta for 0 less than x less than theta. And you have an assumption to test. H naught theta equal 1 versus H1 theta larger than 1. And the rejection rule for the critical region says reject H naught if Y4 is larger than or equal to C. Question is find C for alpha equals 0.05. You know that alpha is the probability of the rejection region. That's it. Probability that Y4 larger than C equals 0.05. How do I find the probability of Y4? On most of the homework assignment that you gave me last time, in the comments I wrote, the distributions of Y1 and Yn are already given in the notes, and you can use them instead of deriving them every time. You don't have that luxury, there's no time. But there are things that you need to memorize and use. So this distribution is given. It is the distribution of x raised to the power 4. So Fy4 equals x over theta raised to the power 4. That's it. And you want that probability that this thing is larger than C given theta equal 1, because that's how you get alpha. Using the non-zero equal 0.5, and then when you plug that in, you get that C to the power 4 is equal to 0.95 because theta is 1. So you solve for C, that's the fourth root of 0.95. And the second question asks for the power function. The power functions differ the same probability now, even for the values of theta that are in the alternative. So that's the same formula you already had here. You don't need to do it again. It's just 1 minus 4 over theta to 4. But you got here that C to the power 4 is 0.95. So that's the power function. Any questions? Is there any question? That's the question. The power function is defined for values of theta in the alternative.
Dr. Longlow,
Yes.
when you said f of y4 of x is equal to f of x to the fourth, is that because it's the maximum?
The distribution of the maximum is the distribution of x raised to the power n.
Okay. And then if it was the minimum, is it just 1 minus that to the n?
Nope.
What was that?
The answer was no.
What is it for a minimum?
How do we find the probability distribution of the minimum? One minus f to the power n. That's the formula for the minimum.
said for the minimum, it's 1 minus x to the n.
1 minus parenthesis 1 minus f to the power n. And if you don't memorize that, then you have to derive it in every single problem where you see that. And it comes all the time. All right, so the next problem said we have x that follows normal between mu and variance sigma squared. And we want to test the hypothesis mu equals 10.1 versus mu larger than 10.1, and the data is given n equals 16, x bar is 10.4, s is 0.4. That's probably the easiest problem I can ask you to do in this class. Test that hypothesis. So t is x bar minus the value you're testing against divided by s over root 9, and you are using t here because sigma is not known, so you have an estimate of sigma. So you put that in, you get t equal 3, and the rejection rule, when the alternative is given as larger than, is t larger than t.05, with, in this case, 15 degrees of freedom, because n is 16 and the degree of freedom is n minus 1. But we got n equal 3 and the t value is 1.753. And you can see evidently 3 is larger than 1.753, and therefore we reject the null hypothesis. And it's asking what find the p-value. P-value is the probability under that same distribution 15 of the value that you found for t, which is 3. So you want probability, same direction as what you have in there, larger than 3. And then you get that is approximately 0.05 using the t table. So the next problem was just sending you to another question that we had earlier, where we build a confidence interval for sigma 1 squared over sigma 2 squared using s1 squared over s2 squared. And the question is telling you, hey, this thing is actually an F distribution. Can you use that to tell us here in this problem, what would C be if the rejection rule says reject if F is larger than or equal to C, where F is that ratio of those I-squares you have here. But here, technically, all you needed to do was to find the degrees of freedom, because they didn't ask you to compute anything. They just asked you to find the C, the critical value for alpha equals 0.05. And so the degree of freedom, it's degree of freedom of the first and degree of freedom of the second, n minus 1, so 12. 11 minus 1, so 10. So the degree of freedom of that F is 12, 10. And you go to that table and you look for 0.05, and you get that it's 2.915 that you're looking for. You can do that, or as you're doing at home, you just put that in the table of F with the 2 degrees of freedom, find the number. That's what I said last time when we were talking about T. When you're doing a homework, you have all the tools. On Google, you have a calculator that gives you the values of the distribution, T, F, Z, whatever you want. For the number, it gives you the probability. And you put the probability, it returns the number as well. In that case, you don't have to look for any extra thing. Any questions on that? And the next question was about our lovely problem that concerns casting a die. So that was cast 120 times independently. We want to test the hypothesis that it is fair, which is P1 equal 16, P2 equal 16, P3 equal 16, all of that. And so I just decided to write P1 equal P2 equal P3 equal P6 equals 16. Right? Versus the alternative, always need to write down, not H, not in this case. Because it could be anything else, it could be something else. No. If it's not this one, not H naught, then you don't have the right to use this formula for that. That's why it's important to always state the null and the alternative before writing it down. The criteria is the test statistic that you're using, because those things are related. Remember, for example, in this first problem, if I don't write down the alternative here, how am I going to define a critical region? So you can't solve a problem that has to do with testing and you don't write down the full alternative. Makes no sense. You need to see H naught, see H1, see your criteria, and see your decisions. And somebody that is reading that would understand, okay, this is the reason why he decided that. And the next problem says, that's what we're talking about. And so we can use the Q here, knowing that here we are not estimating anything, because the null hypothesis says that each of the probabilities is 1/6, so there's no estimation here, which means the degree of freedom of this thing is going to be 6 minus 1/5. And the rejection criteria would be Q5 larger than the high square at the level that is given 0.025, which in this case is 12.83. And you add all these things, that's what you get when you add them. And then all you have to do is solve that inequality, which means this, which means that. After this, you remove the absolute value. How do you remove absolute values from an inequality? You need to know. When it's larger than, it's one thing. When it's less than, it's another thing. Two complete different stories. Here, it's larger than, so that means this number is larger than 11.3, or the opposite of this number, or this number is less than the opposite of that one. And so you solve, you get B less than 8.7, or B larger than 31.3. So here is another big problem. And I kind of explained this last time it happened on a test where people were writing B less than 8 strictly and listing 8 in the options. If you tell me the answer is B less than 8, this is not that. Because this set here includes 8. This one does not. So that needs to be clear. Next time it happens, I take off at least 5 points. The set here that includes 8 is not represented by B strictly less than 8. Inequalities have to be followed as you write them. So if you say this is the case, then the answer has to have or equal here. Send my greetings to the one that is sleeping. So, and then you list the numbers that you get, and that's it. Okay, so please make sure you don't do that. Don't make that mistake. When you're dealing with integers and you're saying strictly less than, even if they are not integers and you're writing strictly less than, you need to know that you're excluding that boundary. That's not part of the set. Now, the next problem was about testing whether data was coming from a Poisson distribution or not. And how were we supposed to do that? They gave us a set of numbers that were obtained for 0, 1, 2, 3. And it asks us to treat everything else as x equal 4. So everything including 3, 4, including 4, 5, 6, 7, 8, all the way to infinity, treat that as x equal 4. Again, we write the formula of the chi-square. In this case, when we write down the formula of the chi-square, we got 5 levels. Which are listed as 0, 1, 2, 3, 4. So sum I from 1 through 5. And it's supposed to be Q4 from the beginning, because that's how we do. Of xi, which is the number of observations that got into x equal I, minus n times the probability divided by n times the probability, where the probability is the probability of that outcome, the outcome being the xi, right? So we don't know them, but we have the assumption that the distribution is chi-square. As for the other problems, we were using the assumption that it's same distribution, and under the assumption that it's same distribution, you find the estimate. In this case, the assumption is the distribution is Poisson. Under that assumption now, you need to estimate these probabilities. Lucky enough, we already know the MLE for lambda, for the Poisson distribution. That MLE is x bar, right? So you can use x bar to estimate lambda. And once you have the estimator of lambda, you plug it into the formula of the probability in the Poisson distribution. And so you will have an estimate of the probability of each of the levels that you have, and your problem is solved. But when you do so, you have estimated one extra thing, right? You have estimated the probability through lambda. You estimated one value, lambda, and use it to estimate everything else. So what you did was one estimation. So that's 1 degree of freedom that is lost. Therefore, the degree of freedom of this thing is going to be 3, not 4. And this gets back to what I was explaining with the difference between the problem where we had 1 and 2, and I was telling you, be careful, don't treat this thing because you're seeing 2 directions as a 2 by 2 table or an A times B table, right? Because when you do so, you lose the meaning of the thing. In this case, you can't say it's chi-square 4 because I added 5 things and then I need to remove 1. That's where you start. And then after that, everything that you estimate inside there loses 1 degree of freedom. And that's why in the other formula, we went from 2k minus 2 down to k minus 1. And in this case, it's just 1 because we estimated only lambda and then used it to get the other values. Therefore, the DF is 3. So you compute this thing using these formulas to get the PIs, and you get that your Q4 is approximately 7.23. And your criterion would be reject H naught if Q4 is larger than chi-square 3.05 at that level, which is 7.815. And you want to say I would reject if 7.23 is larger than 7.815. And in this world in which we are living, that's not true. Right? So we don't have enough evidence to reject H naught in this problem. So the data seems, carefully how I say, the data seems to be coming from a Poisson distribution. I'm not saying that it's coming from that Poisson distribution, because I can't certainly say that. I'm not sure. As you have 5% chance of being wrong, which is the reason why I keep telling you, I never accept a thing because you don't have all the information. There is always a chance to be wrong. Maybe this is a bad example, but I take it anyways. During the last, not the last, but the elections before the last one, all polls in this country were claiming that one person would win the vote with a certain margin. That person lost. And somehow, instead of just explaining to the public that that's the reason why there is always a margin of error, there were all sorts of claims. In their study, there was the chance that the other candidate would win, but they never explained that. That's why you need to be very careful when you're doing statistics and making a decision. Tell the person, yeah, I'm telling you this, but you know, 95% sure that it's gonna work. But 5 times out of 100, this thing is gonna be wrong. That's a fact. And that election turned out to be one of those. At the scientific take on that, no matter which party you belong to. Now, back to this. We have questions here. Is there any question at this point? Is there any question on these testing questions? I perfectly understand. I'm wondering why you're not taking any notes. Huh? It's quite surprising. Next. The next problem, and that's where I was asked at the beginning of the lecture to talk about distribution. That's where we are. So, the first question is, you have a random sample, x1, x2 up to xn, from a distribution x that has PDF, e to negative x minus theta, and 0. For x larger than theta, theta between negative infinity and infinity. And then yn is the minimum of x1 all to xn. And then you have to show that yn converges to theta in probability. How do you show that? Can you use the distribution of yn, which we know. Here in this case, yn is defined as the minimum, not the maximum. So the distribution of x, this is the distribution that we already know, it's just shifted. So it's 1 minus e to negative x minus theta for x larger than theta. So the distribution of the minimum is 1 minus the distribution of the random variable we have raised to the power n. And that's what we have here. It becomes 1 minus e to the negative n times x minus theta for x larger than theta. Now here's where we need to be very careful, as I explained last time. You are working for all epsilon larger than 0. You want to find the probability that absolute value of yn minus theta is larger than or equal to epsilon. If you want to flip this thing, it has to be strictly less than epsilon. And the way I actually advise to take notes when I don't collect your homework on paper is you still have your homework when I'm showing you the answers. So you can look at your homework and put the notes on the places that are different from what you did. That's the best way to do that, because when you look back at what you did, you know what the difference was. Now, for this probability, I switch. I said, okay, because larger than or equal, it's 1 minus probability, and this is what I'm talking about. Here it becomes strictly less than. It might matter in a different problem. This is 1 minus probability, and then I remove the absolute value, and now get this. But when I remove the absolute value and get this, I can see that theta minus epsilon is less than theta. So it's not going to be covered. This thing is going to stop at theta. Therefore, it's going to be 1 minus probability that theta is less than yn, less than theta plus epsilon. And this probability is capital F of theta plus epsilon minus capital F of theta. Right? That gives you 1 minus, and the capital F is 1 minus, so the ones cancel, the minus cancels with the other minus, and capital F of theta is 0, so the answer is just e to negative n times epsilon. And in this case, because you have an equality, not an inequality, you can just compute the limit is equal to the limit of e to negative n epsilon, and epsilon is positive, therefore that limit is 0, which means that yn converges in probability to theta. Questions? That's the definition. And all these questions are about using the definition. You need to read it first. Always read your notes before starting to do problems. Now the next problem, I chose the next problem from the same distribution, so you don't have to get the distribution again from somewhere else. So the same question, same distribution. Sample size n, same distribution. And then Zn is defined as n times y1 minus theta. And the question is, what's the limiting distribution of Zn, which means what's the limit of Z, what does Zn converge to in probability? And so the distribution of capital Yn was given in the problem up here. So we just copy it down. And then we find the probability, the CDF of Zn. What's the CDF of Zn? It's the CDF of Yn at the point x over n plus theta. How? Just write probability that Zn less than x and solve for y1. And so you get this, and then you plug it into the formula of y1 that you have here. That's 1 minus e to the negative n times x here is x over n plus theta minus theta. The thetas cancel, the n's cancel, and you get that Zn, no matter what is n, Zn has distribution 1 minus e to the negative x. It doesn't matter what n is. So Zn is actually independent of n. That random variable is always exponential. So Zn follows the exponential 1, and if it's exponential 1 for all n, then the limit is the same, exponential 1. There's no need to take any limit. Questions on this one? This is like for real numbers saying 3 converges to 3, because 3 is 3, it doesn't change.
Dr. Longla, can you move the paper up, or is that the next problem?
It's finished here.
Thank you.
Okay, so the next problem is about any distribution. So you just have some distribution, capital F, and we want to find the limiting distribution of Zn equals n times 1 minus capital F of Yn, where Yn is again the maximum of the observations. How do you find the limiting distribution? Again, the maximum, the distribution of the maximum is capital F of x raised to the power n. F of Zn, how do I find F of Zn? I took the paper on the side, just write that for those who not understand why I wrote that. So that's Zn, probability that Zn is less than x, that's it. You just write that down and then you solve for Yn. You find that that means that Yn is larger than F inverse of 1 minus x over n, because you got capital F of Yn larger than 1 minus x over n. Why can I do this? The CDF is a non-decreasing function, right? You need a justification to go from here to here. And I'm saying the justification would be that the CDF is a non-decreasing function. Therefore, if it's increasing and I apply the inverse, yn will have to be larger than that. And this, from here, you just get that this would mean if I'm taking probability of this thing, that would be 1 minus, because it's larger than 1 minus Fyn of what? The thing that is right here, which is this. Now all you have to do is to apply Fyn to this. That's where you apply Fyn to what is inside. And Fyn is this. F of x raised to the power n. So f of the whole thing that is inside here, f of this whole thing, that's it. F of that whole thing raised to the power n. Now when you do that, inside here, what you have is capital F of f minus 1 of 1 minus x over n. And this is the inverse of that function. If you compose a function by its inverse, you get it the identity. So this is just 1 minus x over n. Therefore, raising it to the power n, you get this. And if you take the limit of this thing, several times already we had that in this class, the limit of this part is e to negative x. So that's 1 minus e to negative x, and it's with x greater than 0. Again, that same distribution that we got up there, exponential with 1 degree of freedom. I'm sorry, with parameter 1. Questions? So next problem. Just keep this here. So that's your next problem. It says Xn follows the gamma distribution with parameters n and beta. And we define Yn equals Xn divided by n. And the question is, find the limiting distribution of Yn. And that question is in this section of the moment generating function technique, which means use the moment generating function to answer this question. So you have to find the moment generating function of this random variable. That is equal to the moment generating function of Xn at the point t over n. And we know the moment generating function of Xn, it is 1 minus beta t raised to the power alpha. And then we replace that t by t over n, so we get 1 minus beta t over n raised to the power n. And we take the limit. When we take the limit, the same rule we applied in the previous problem works. The limit of this function is e to the beta t. So the moment generating function converges to e to the beta t, and this e to the beta t is the moment generating function of the random variable that ym converges to. And the question is, what random variable is this and why? What's the random variable that has moment generating function e to the beta t? Can you explain it to me why? That's a question for everybody.
Can you ask it again?
What's the random variable that has distribution e to the beta t? Because we don't yet have that distribution. The question was find the limiting distribution. What we found is the moment generating function. And what's the limiting distribution? What distribution gives you this? What's the random variable that has this moment generating function e to the beta t?
The volume.
Shouldn't have n because it's the limit.
Characteristic function,
Hmm?
indicator function. So here it is like indicator function.
Why the indicator function? The easiest possible things, you guys always try to make them difficult.
Standard legendary distribution.
If you're talking the indicator function, what are the possible values of the indicator function?
1 and 0.
1 and 0. Now look at that guy, e to the beta times t. How would you get e to beta t from 1 and 0? Finding them all.
And beta equal to 1.
Beta is not part of 1 or 0. 1 or 0 is just the indicator function. That x is equal to beta. Well, then technically I just gave you the answer. So the only random variable that has moment generating function e to the beta t is beta, the constant. And this is what you were actually asked to do. If you stop here, you're not done. And why would that be the case? Well, what's the definition of the moment generating function? Term x of t equals expected value of e to the tx, right? Isn't it? Are we in agreement? Okay. Now, if x equals beta, with probability 1. What is this? Expected value of e to the t beta. What is this? And you also know that you can't have two different random variables with the same moment generating function. So it's the only one. Now, on the other side, you could actually find this answer after getting here. You could find this answer even if you didn't know that the moment generating function of the constant beta is e to the beta t. How would you do that? It is for a reason that they made alpha the parameter that is equal to n. When that parameter is equal to n, what does it mean? One of the theorems that we prove for gamma distribution, when we add two gamma distributions, what do we get? With two gamma distributions with the same beta. Hmm?
They can be sum of the constant.
Huh? I didn't get what you said.
If two distributions are equal up to a constant, it means that they are from same distribution.
No, that's not what I'm asking about. I'm asking if I take two independent gamma distributions with the same parameter beta and different alphas, what do I get? And theorem we have in the notes about it. We get gamma with alpha plus beta and alpha 1 plus alpha 2 and beta, which is the justification actually of this thing. So an alternative could be that yn is actually equal to 1 over n times x1 plus x2 plus xn, not this xn that is here. Let's say call them differently so you won't think where zi's are independent. Gamma 1 beta. If I add n independent gamma 1 beta, which is exponential, then I obtain this, which is a gamma with n and beta. So this is true based on that theorem that is in your notes. Therefore, actually, yn that is given in this problem is nothing but z bar. And this is z bar, expected value of z equals beta, because it's alpha times beta. Alpha is 1. Variance of z is finite. I don't want to know what it is, but it's finite. So by the weak law of large numbers, cancel that whole figure. Z bar converges in probability to expected value of z, which is beta. So So Z bar converges in probability to beta. And Z bar is Yn. And from the other problem that you had, if it converges in probability to beta, then it converges in distribution to beta. That's the other theorem that you have. So without using that, I could still prove that Yn converges in distribution to beta. So it's going to be all up to what we want to memorize. Now, I have another funny question here. This is the time for you to solve the problems. Let's say we have a problem, xn cn follows I squared with n degrees of freedom. And I want you to get the distribution. Limiting distribution. Wn equals Zn n. You can use any technique that you want. There are many such problems on that page. You can solve any of them. Anyone with the answer? Got it? you done with question? There are many methods you can use, anyone. Anyone with the answer? So what is the answer? One? Why would it be, why you get one? Ju- Justify your answer.
Two more generating function.
Okay, what is the moment generating function equal to?
1 minus 2 d to the minus m of t. Of s square.
Y minus n over two? Then you take the limit. So, first of all, as we are going there, I need to remind you something. There was a typo here. This power is minus n, not n. That's why the answer is e to beta t. Otherwise, it would be e to minus beta t. But because of that minus here, that's the reason why it was correct. But I was missing this minus. Now, coming back to this question, and that was correct. So the moment generating function, we can use the moment generating function technique here. And so on. Wn of t equals m Zn of t over n, which is equal. The moment generating function of high square is 1 minus 2 times the variable, that's t over n, raised to the power minus degree of freedom over 2 minus. Right? Why is that? Because the high square is actually also a gamma distribution. And the limit of this when it converges, what do you think it is? The number n over 2 here is the one that is flipped there. Minus compensates the minus that is here, so you get e to the t. So this moment generating function converges to e to the t, and therefore that would mean that Wn converges in distribution to 1. Answer 2. The alternative was what I just did in the previous problem. You can do the same thing here and say Wn is 1 over n times x1 plus this xn, where xi's are independent, identically distributed. I square 1, because you know that the sum of independent high squares gives you a high square with the sum of degrees of freedom. So if you add n of them, and you obtain the high square n that is given here. Therefore, that means Wn is nothing but x bar again. And by the weak law of large numbers, Wn converges to expected value of x, and the expected value of I square 1 is 1. Wn converges in probability to 1. This conclusion is convergence in probability, but you were asked about convergence in distribution, and you use the theorem that states that if you have a random variable that converges in probability to a constant, then it does converge in distribution as well to the same constant. That's it. Questions? Now, after this funny one, let me change a little bit this problem. Let's say Qn for the last 5 minutes is equal to Zn over n squared. That same Zn. The same Zn that we have here. Find, same question, find the limiting distribution. And in this case, you can no longer use this idea because it is not more an average, which is the reason why you need to know the other way.
Why can't you use that?
That's not an average. And that theorem works exclusively for the average.
Oh, and
So from time to time, there are some little tricks like that in those questions. And if you don't read carefully, you jump in and start doing something that is not appropriate. You need to read carefully the question. Got the answer?
Is that zero?
He says it's zero. Who else thinks it's zero? You think so?
Sure.
You think it's zero too? Okay, so what you guys got at the moment generating time? Answer. So MQM of T equals what? Should be easy. Listen. T over N squared, that's the usual thing, which is? Raised to the power. Why would that be N squared? Well, it's be N squared. It's N over 2. The power has nothing to do with what you're plugging in here. That's alpha. So the alpha is N over 2 for the square distribution. The 2 here is for the beta, which is 2 for the I square beta is 2. And so what is this limit equal to? I'm worried. Huh? What's that? I can't be what you said. Yeah, what is the limit equal to? This thing goes to what? It's a sequence. What's the limit? Based on your own answer that you already gave me, you can guess what that limit is.
Can you do it without moment generating function?
This is the topic. Huh? What do you mean you don't sure? This limit is curve 3. Huh?
Thinking, just thinking, limit is used by
a limit cannot contain n. What? One, thank you. And I actually said, based on your own answer that you already gave me, you should know what the answer is, because you said it converges to zero. If it converges to zero and it is e to the constant and t, then what should it be? The moment generating function. It should be one. So even if you didn't use this method, you would know that the moment generating function will converge to one. Right?
But we can do that. Z in our n goes to 1, right?
Mhm.
And 1 over n goes to 0.
That's if you're assuming you have this answer in front of you.
Yeah.
But if I give you this question and you don't have that first part in front of you, as I'm answering the question as if this doesn't exist. Okay? If this was right there in front of me, I would say, as he's saying, 1 over n goes to 0, and z over n goes to 1, so it goes to 1 times 0 equals 0. That's it. So, and please, when you get home, check why this limit is equal to 1. Okay. Therefore, Qn converges in distribution to 0 because 0 is the only random variable with moment generating function equal to 1. And that's it for today. Thank you very much for showing up. And I see you on Wednesday on the test.